Hi everybody, welcome back to our video lecture on the respiratory system. This is the third part of the lecture, which is an extension of the physiology, and in this section of the notes we will focus on the gas exchange that happens between the blood, lungs, and tissues. Last time we outlined the importance and distinction between external respiration and internal respiration. We said that external respiration happens in the lungs, and it's the diffusion of both gases, whereas internal respiration happens in the tissues, and likewise it's the diffusion of both gases, whereby carbon dioxide is going to leave the cells and oxygen has to enter the cells. We also looked at Boyle's law last time, which helped us understand the pressure, how pressure is inversely proportional to volume. Thereby, when you are increasing the volume of your thoracic cavity, the pressure is going to drop, and vice versa. When the volume is going to decrease, the pressure goes up, and this is really what enables for air to move in and out of the thoracic cavity. So let's move over now and talk about two other laws which are going to help us understand what happens when gases are moving in a solution. You can think of our solution, of course, as blood. Inside the blood vessels, you have blood plasma, you have the constituents of blood that are flowing through the body, in addition to the gases. So the first law is Dalton's law of partial pressures, which states that the total pressure exerted by a mixture of gases is the sum of the pressures exerted independently by each gas in a mixture. And further, the pressure exerted by each gas is known as its partial pressure. So this is directly proportional to the percent of that gas in the mixture. We see from this table that nitrogen makes up roughly about 79% of air, and the partial pressure of nitrogen is 78.6%. So when you multiply that times the atmospheric pressure, which is 760 millimeters of mercury, you end up with a partial pressure of nitrogen being 597 millimeters of mercury. Oxygen accounts for about 21% of air, and its partial pressure is 159 millimeters of mercury. So how do you get this 159? You would multiply the 20.9% times the atmospheric pressure, which is 760 millimeters of mercury, and then you end up with 159 millimeters of mercury. So together, nitrogen and oxygen contribute about 99% of the total atmospheric pressure. Air also contains about 0.04% carbon dioxide, about 0.5% water vapor, which these are well-known greenhouse gases in the atmosphere. It's important to note that at high altitudes, partial pressures decline in direct proportion to the decrease in atmospheric pressure. So as an example, at 10,000 feet above sea level, where the atmospheric pressure is 523 millimeters of mercury, the partial pressure of oxygen is only 110 millimeters of mercury. Let's move over to the second law, which is Henry's law. And this law states that when a gas is in contact with a liquid, the gas will dissolve in the liquid in proportion to its partial pressure. So accordingly, the greater the concentration of a particular gas in the gas phase, the more and the faster that gas will go into solution in the liquid. Furthermore, at equilibrium, the partial pressures in the gas in the liquid phase are the same. If, however, the partial pressures of the gas later becomes greater in the liquid than in the adjacent gas phase, some of the dissolved gas molecules will re-enter the gaseous phase. Thereby, the direction and amount of movement of a gas are determined by its partial pressure in the two phases. So this flexible situation is exactly what occurs when gases are exchanged in the lungs and also in the tissues. For example, when the partial pressure of carbon dioxide in the pulmonary capillaries is higher than in the lungs, carbon dioxide is going to diffuse out of the blood and then enter the air in the alveoli. Now, how much of a gas will dissolve in a liquid at any given partial pressure also depends on the solubility of the gas in the liquid and the temperature of the liquid. The gases in air have very different solubilities in water and therefore in the blood plasma. So for example, carbon dioxide is most soluble, as it is 20 times more soluble in water than oxygen. For this reason, at a given partial pressure, much more carbon dioxide than oxygen dissolves in water, and particularly no nitrogen gas. It's going to dissolve into a solution. When a liquid's temperature rises, gas solubility decreases. So think of a club soda, which is produced by forcing carbon dioxide gas to dissolve in water under high pressure. If you take the cap off a bottle of club soda and leave it in the fridge, it will slowly go flat. But if you leave it at room temperature, it will very quickly go flat. So in both cases, you end up with plain water. All the carbon dioxide has escaped from the solution. And some of you have heard of the hyperbaric oxygen chambers, which really provide clinical applications to Henry's laws. These chambers contain oxygen gas at pressures higher than 1 atmospheric and are used to force greater than normal amounts of oxygen into the blood of patients suffering from carbon monoxide poisoning or tissue damage following radiation therapy. Hyperbaric therapy is also used to treat individuals with gas gangrene because the anaerobic bacteria causing this infection cannot live in the presence of the oxygen levels. Therefore, scuba diving provides another illustration of Henry's laws. If divers rise rapidly from the depths, dissolved nitrogen forms bubbles in their blood, causing what, quote unquote, we know of as the bends. So a clinical homeostatic imbalance is that although breathing oxygen at 2 atm is not a problem for short periods, oxygen toxicity develops rapidly when the partial pressure of oxygen is greater than 2.5 to 3 atm. So excessively high oxygen concentrations generate huge amount of free radicals, resulting in profound disturbances to the central nervous system, which can elude or lead to coma and even death. So as we saw earlier from this table, the gaseous makeup of the atmosphere is quite different from that in the alveoli. The atmosphere is almost entirely oxygen and nitrogen based. However, the alveoli contain more carbon dioxide and water vapor and much less oxygen. So these differences reflect the effects of three things. Number one, the gas exchange occurring in the lungs, meaning oxygen diffuses from the alveoli into the pulmonary blood and carbon dioxide diffuses in the opposite direction. The second one is the humidification of air by conducting passages. And the last one is going to be the mixing of alveolar gas that occurs with each breath, because only about 500 milliliters of air enter into each tidal inspiration. Gas in the alveoli is actually a mixture of newly inspired gases and gases remaining in the respiratory passageways between breaths. The alveolar partial pressure of oxygen and carbon dioxide are easily changed by increasing breathing depth and rate. Now we're going to move over and look at some of the factors that are going to influence external respiration. We said that external respiration is the exchange of both of these gases across the respiratory membrane, and this happens in the lungs. So we're going to outline these three factors: the thickness and surface area of the respiratory membrane, partial pressure gradients and gas solubilities, and finally the concept of ventilation and perfusion. So let's begin with the thickness and surface area of the respiratory membrane. In a healthy lung, the respiratory membrane is about 0.5 to 1 micrometers thick, and gas exchange is usually very efficient. And the greater the surface area of the respiratory membrane, the more gas can diffuse across in a given time period. In healthy lungs, the alveolar surface area is enormous. So if we spread this flat, the total gas exchange surface of these tiny sacs in an adult male's lung is about 90 meters squared, which is approximately 40 times greater than the surface area of the skin. So that's highly impressive. A homeostatic imbalance that may be referenced in your chapter is that certain pulmonary diseases drastically reduce the alveolar surface area. So for instance, with emphysema, the walls of adjacent alveoli break down and the alveolar chambers enlarge. So tumors, mucus, and inflammatory material can also reduce surface area by blocking gas flow in the alveoli. So let's go over to the second factor that can affect external respiration, and this is the partial pressure gradients of the gas solubilities. Partial pressure gradients of oxygen and carbon dioxide drive the diffusion of these gases across the respiratory membrane. So a steep oxygen partial pressure gradient exists across the respiratory membrane because the partial pressure of oxygen in deoxygenated blood in the pulmonary arteries is only about 40 millimeters of mercury, as opposed to the partial pressure of approximately 104 millimeters of mercury in the alveoli. So as a result, oxygen is going to diffuse rapidly from the alveoli into the pulmonary capillary. So this subscript that you're seeing here, the P stands for the partial pressure, and of course you probably guessed it that this would be the partial pressure of oxygen, and then vice versa. If you see CO2, it would be the partial pressure for carbon dioxide. So this is what we're illustrating in the image. You're seeing that the partial pressure of these gases is really what drives the diffusion of the gases. So notice that the partial pressure for carbon dioxide is 45 millimeters of mercury as it enters the lungs, and the partial pressure in the alveoli of carbon dioxide is 40 millimeters of mercury. Therefore, diffusion goes from high to low concentration. Since you have a higher concentration of carbon dioxide in the blood, carbon dioxide diffuses out and it enters the alveolus, and then you exhale that out. Likewise, notice the partial pressure for oxygen in the blood or in the lungs, and notice the partial pressure of oxygen in the alveolus. So this partial pressure is higher in the alveolus than that of the blood. Therefore, oxygen is going to leave the alveolus, enter the pulmonary capillaries as carbon dioxide is leaving. So as carbon dioxide diffuses in the opposite direction along a much gentler partial pressure gradient of about 5 millimeters of mercury, you could see this 45 millimeters of mercury against 40 millimeters of mercury, expiration then gradually expels carbon dioxide from the alveoli. Even though the oxygen pressure gradient for oxygen diffusion is much steeper than that of carbon dioxide gradient, equal amounts of these gases are actually exchanged. And why is that? Well, remember, the reason is that carbon dioxide is 20 times more soluble in plasma and in alveolar fluid than oxygen. So now what we need to do is move over to the last factor influencing the external respiration. We're going to look at ventilation-perfusion coupling. For optimal gas exchange, there must be a close match, or what we call coupling, between ventilation. Ventilation really is the amount of gas reaching the alveoli, and perfusion, which is the blood flow in the pulmonary capillaries. So both are controlled by local autoregulatory mechanisms that continuously respond to local conditions. So for the most part, the partial pressure of oxygen controls perfusion by changing arteriolar diameter, whereas the partial pressure of carbon dioxide controls ventilation by changing bronchiolar diameter. So let's take a look at this image, which is going to help us understand how the partial pressure of oxygen controls perfusion by changing arteriolar diameter. So if the alveolar ventilation is inadequate, local partial pressure of oxygen is low, because blood takes oxygen away more quickly than ventilation can replenish it. As a result, the terminal arterioles are going to constrict. When they do that, they redirect blood to respiratory areas where the partial pressure of oxygen is high and oxygen pickup is more efficient. When alveoli ventilation is maximal, high partial pressure of oxygen dilates pulmonary arterioles, and blood flow into the associated pulmonary capillaries increases. Notice that the autoregulatory mechanisms controlling pulmonary vascular muscle is the opposite of the mechanism controlling arterioles in the systemic circulation. And so by changing the arteriolar diameter, whether it be that you're constricting or dilating, this directs most blood where alveolar oxygen is higher. Now let's take a look at the influence of local partial pressure of carbon dioxide on ventilation, bronchial servicing areas where alveolar carbon dioxide levels are high dilate, allowing carbon dioxide to be eliminated from the body more rapidly, bronchial serving areas where partial pressure of carbon dioxide is low are going to go ahead and constrict, which allows elimination of carbon dioxide more rapidly. So it's interesting that the changing diameter of local bronchioles and arterioles synchronizes alveolar ventilation and pulmonary perfusion. Poor alveolar ventilation results in low oxygen and high carbon dioxide levels in the alveoli. Consequently, pulmonary arterioles constrict and airways dilate, bringing blood flow and airflow into closer physiological match. High oxygen partial pressure and low carbon dioxide partial pressure in the alveoli cause bronchioles serving the alveoli to constrict and promote flushing of blood into the pulmonary capillaries. Now that we've taken a look at the factors that influence external respiration, let's move over to internal respiration, which involves capillary gas exchange in body tissues. In or during internal respiration, the partial pressures and diffusion gradients are reversed from the situation that we just described in this image. So we were focusing on external respiration. Now let's take a look at internal respiration. Tissue cells continuously use oxygen for their metabolic activities and produce carbon dioxide. So because the partial pressure of oxygen is always lower in tissues than it is in the systemic arterial blood, notice that this is 40 millimeters of mercury versus 100 millimeters of mercury. Oxygen moves rapidly from blood into tissues until equilibrium is reached. At the same time, carbon dioxide moves quickly along its pressure gradient into the blood. So as a result, venous blood draining the tissue's capillary beds and returning to the heart has a partial pressure for oxygen of 40 millimeters of mercury, and the partial pressure of carbon dioxide is the 45 millimeters of mercury. So in summary, as we transition into the next part of our lesson here, the gas exchanges that occur between blood and the alveoli and between blood and the tissue cells take place by simple diffusion. So they're driven by partial pressure gradients of oxygen and carbon dioxide that exist on the opposite sides of the exchange membranes. So now we're going to take a close look of how both oxygen and carbon dioxide are transported in the blood. There are two ways that molecular oxygen is carried in the blood. The first way is that it's bound to hemoglobin within red blood cells, and the second way is that it's dissolved in blood plasma. So oxygen is poorly soluble in water, so only about 1.5% of the oxygen transported is carried in the dissolved form. And notice that the majority of the way oxygen is transported is bound to the hemoglobin protein. We described the nature of hemoglobin protein in a previous lecture video. We said that there are up to 4 oxygen molecules that can be bound to one hemoglobin protein, and that's because the oxygens have what we call an affinity to the hemoglobin because of the iron binding group. So this iron binding group is going to attract up to 4 oxygen molecules. The hemoglobin-oxygen combination is called oxyhemoglobin, and it's typically denoted this way, so HbO2. Hemoglobin that has released oxygen is called reduced hemoglobin or deoxyhemoglobin, and is typically written H, capital H, capital H, B. A single reversible equation describes the loading and unloading of oxygen. So when you have the deoxyhemoglobin that binds to oxygen, or we should say that oxygen binds to deoxyhemoglobin, we know this as the loading of oxygen. I like to think of oxygen kind of like passengers on a taxi cab, and the hemoglobin protein is the taxi cab. So when the taxi cab, or nowadays you have Lyft and Uber, is going to pick up those passengers, i.e. the oxygen, we know this as loading. And likewise, when the hemoglobin protein arrives at the tissues where the oxygen is needed, then we say that oxygen unloads. So the unloading of oxygen is going to result in deoxyhemoglobin, and the loading of oxygen happens in the lungs, and that's what causes or enables for oxyhemoglobin to be formed. Additionally, when 1, 2, or 3 oxygen molecules are bound, a hemoglobin molecule is partially saturated. When all 4 of its heme groups are bound to oxygen, the hemoglobin is fully saturated. So by the same token, unloading of one oxygen molecule enhances the unloading of the next, and so on. In this way, the affinity, or the binding strength, of hemoglobin for oxygen changes with the extent of oxygen saturation, and both loading and unloading of oxygen are very efficient. Now, the rate at which hemoglobin reversibly binds or releases oxygen is regulated by the factors that you see here: the partial pressure of oxygen, temperature, blood pH, the partial pressure of carbon dioxide, and also the blood concentration of BPG, which is an organic chemical, and this organic chemical is produced by red blood cells during glycolysis. These factors interact to ensure that adequate oxygen is delivered to the tissue cells. Now what we want to do is move over and explain the oxygen hemoglobin dissociation curve that really shows how local partial pressures of oxygen controls oxygen loading and unloading from hemoglobin. So let's take a look at this image, and as we walk through this graph step by step, we're going to explain how hemoglobin ensures adequate oxygen delivery under a variety of conditions. Now, under normal resting conditions, the partial pressure of oxygen is said to be at 100 millimeters of mercury. Arterial blood hemoglobin is 98% saturated. So you see on the graph here that on the x-axis we see the measurements or the partial pressures of oxygen, whereas on the y-axis we see the percent oxygen saturation of hemoglobin. So we see that in the lungs, where the partial pressure for oxygen is high at the 100 millimeters of mercury, hemoglobin is almost at 100%, or it's almost fully saturated with oxygen. In the tissues, on the other hand, the partial pressure for oxygen is low, and we said that was 40 millimeters of mercury, and the hemoglobin protein is less saturated. It's less saturated at 75% with oxygen. Let's take a look at this, which is comparing the saturation of hemoglobin at sea level versus the saturation of hemoglobin in high altitude. So in high altitude, even though there's less oxygen available, at a partial pressure in the lungs of only 80 millimeters of mercury, hemoglobin is still 95% saturated. So what this tells us is that hemoglobin's properties produce a safety margin that ensures that hemoglobin is almost fully saturated, even with a substantial decrease in the partial pressure of oxygen. So as a result, hemoglobin remains saturated even at high altitude or when you have things such as lung disease. We mentioned earlier that there are various factors that influence hemoglobin saturation. We mentioned temperature, blood, pH, partial pressure of carbon dioxide, and the amount of BPG in the blood. Red blood cells produce BPG as they metabolize glucose. BPG binds reversibly with hemoglobin, and its levels rise when oxygen levels are chronically low. So all these factors influence hemoglobin saturation by modifying hemoglobin's three-dimensional structure, thereby changing its affinity for oxygen. So anytime you have an increase in temperature, you have an increase in acidity of the blood, meaning that you have a low pH, or BPG levels in blood lowers hemoglobin's affinity for oxygen, it's going to enhance oxygen unloading from the blood. So this is shown by rightward shift of the oxygen hemoglobin dissociation curve that we see depicted in this image. So we're looking at the partial pressure of oxygen on the x-axis and the percent oxygen saturation of hemoglobin on the y-axis. Looking at body temperature as an example, if we use normal body temperature of 38 degrees Celsius, when the body temperature decreases, the oxygen hemoglobin dissociation curve is going to shift to the left. When body temperature increases, the curve is going to shift to the right. Likewise, when we look at the carbon dioxide values, normal arterial carbon dioxide, we learned, is 40 millimeters of mercury. And in a moment, we're going to see how level of carbon dioxide is going to alter or affect the pH. In other words, when you have a higher carbon dioxide, that means that you have more protons in the blood, meaning that the pH is going to become lower or more acidic. Notice that when you have a lower acidity, meaning that there's more carbon dioxide, so more carbon dioxide is going to drive the pH from 7.4 to 7.2. So this is what we mean by the from hemoglobin. Anytime you have an increased temperature, you have increased carbon dioxide levels and or hydrogen ion concentration, as we noted here, causing the dissociation curve to shift to the right. Conversely, when you have a decrease in any of these factors, such as temperature or decreased carbon dioxide, these factors are going to increase hemoglobin's affinity for oxygen, meaning that you will have a decrease oxygen unloading. So this change shifts the dissociation curve to the left. So one thing to consider is that these factors are related. You'll realize that they all tend to be highest in the systemic capillaries, meaning that you have higher carbon dioxide in the systemic capillaries, where oxygen unloading is the goal. So as we get into the tissues, because the partial pressure of oxygen is less and there's a greater content of carbon dioxide, we want to facilitate that oxygen unloading by hemoglobin, meaning you want to remove or you want to get rid of those passengers, if you will. As cells metabolize glucose and use oxygen, they release carbon dioxide, which increases the partial pressure of carbon dioxide. And the proton levels in the capillary blood, remember what we said about increased partial pressure of carbon dioxide, that means that you have more protons, thereby more acidity, or the pH is going to be lower. Both declining blood pH, which is known as acidosis, and increased partial pressure of carbon dioxide is going to weaken the hemoglobin saturation, or the hemoglobin to oxygen saturation. And this phenomenon is what we know of as the Bohr effect. So anytime you have an increased carbon dioxide, which leads to a decline in blood pH, these factors are going to weaken that saturation or the bond between the hemoglobin and oxygen. And that's a good thing. It's a good thing because we want to unload these passengers. We want to make sure that oxygen goes to the tissues where it's used, and this is what we know as the Bohr effect. So before we leave off the transport of oxygen, or how oxygen is transported in the blood, let's look at some homeostatic imbalances. Inadequate oxygen delivery to body tissues, a lot of you know, is called hypoxia. So hypoxia is more visible in fair-skinned people because their skin and mucosae take on a bluish kind of cast. When hemoglobin saturation falls below 75%. So in dark-skinned individuals, this color change can be observed only in the mucosae and in the nail beds. Hypoxia is classified based on the cause. You can have anemic hypoxia, which reflects poor oxygen delivery resulting from too few red blood cells or from red blood cells that contain abnormal or little hemoglobin. You can also have histotoxic hypoxia, which occurs when blood cells are unable to use oxygen even though adequate amounts are delivered. Metabolic poisons such as cyanide can cause histotoxic hypoxia, and you can also have hypoxemic hypoxia, which is indicated by reduced arterial partial pressures of oxygen. And the last one is carbon monoxide poisoning, which is a unique type of hypoxemic hypoxia and a leading cause of death from fire. So carbon monoxide is an odorless, colorless gas, as some of you know, and because of hemoglobin's affinity for carbon monoxide is actually 200 times greater than its affinity for oxygen, carbon monoxide outcompetes oxygen for the heme binding sites, and that's what results in the poisoning, if you will, which is going to cause respiratory distress. So the victim feels confused and has throbbing headaches, and in rare cases the skin becomes cherry red. Patients with carbon monoxide poisoning are given hyperbaric therapy if available, or 100% oxygen until the carbon monoxide has been cleared from the body. So let's move over now to how carbon dioxide is transported in the blood. So normally active body cells produce about 200 milliliters of carbon dioxide each minute, exactly the amount excreted by the lungs. Blood transports carbon dioxide from the tissue cells to the lungs in three forms. We have dissolved in plasma, which is about 7 to 10%. This is the smallest amount of carbon dioxide. The second one is chemically bound to hemoglobin, which is about 20%. Dissolved carbon dioxide is bound and carried in the red blood cells as carbonoamino hemoglobin. And finally, you have the last one, which is the majority, and this is 70%, where carbon dioxide is transported as bicarbonate in plasma. So most of the carbon dioxide molecules entering the plasma enter red blood cells. The reactions that convert carbon dioxide to bicarbonate ions for transport mostly occur inside the red blood cells, as you see in this image here. When dissolved carbon dioxide diffuses into the red blood cell, it combines with water, forming carbonic acid, or H2CO3. Carbonic acid is an unstable compound and dissociates, means that it splits, and this dissociation forms the bicarbonate ion and the hydrogen ions, which is the same equation that we saw here. So although this reaction occurs in the plasma, it is thousands of times faster in red blood cells because they contain carbonic anhydrase. The blood plasma does not contain the enzyme carbonic anhydrase. So this enzyme reversibly catalyzes the conversion of carbon dioxide and water to carbonic acid. Hydrogen ions released during the reaction, as well as carbon dioxide itself, bind to hemoglobin, and this is what's going to trigger the Bohr effect. So in this way, carbon dioxide loading enhances oxygen release. So because of the buffering effect of hemoglobin, the liberated protons cause little change in pH under resting conditions. So as a result, blood becomes only slightly more acidic, and it declines from 7.4 to 7.34 as it passes through the tissues. So once generated, the bicarbonate moves quickly from the red blood cells into the plasma, where it is carried to the lungs. To counterbalance the rapid outrush of these anions from the red blood cells, chlorine ions move from the plasma into the red blood cells. So this ion exchange process is known as the chloride shift, which occurs via facilitated diffusion through in red blood cell membrane protein. In the lungs, if we take a look at the similar image here in the lungs, the process is reversed. As blood moves through the pulmonary capillaries, its carbon dioxide partial pressure declines from 45 millimeters of mercury to 40 millimeters of mercury. For this to occur, carbon dioxide must first be freed from its bicarbonate housing, so to speak, bicarbonate then re-enters the red blood cell. And chloride moves out into the plasma and binds with a proton to form carbonic acid. Carbonic anhydrase then splits carbonic acid to release carbon dioxide and water. So this carbon dioxide, along with that released from hemoglobin and from solution in plasma, then diffuses along its partial pressure gradient from the blood into the alveoli. And the amount of carbon dioxide transported in blood is affected by the degree to which blood is oxygenated. So the lower the partial pressure of oxygen and the lower the hemoglobin saturation with oxygen, the more carbon dioxide that blood can carry. So this phenomena is known as the Haldane effect, which reflects the greater ability of reduced hemoglobin to form carbonaminoglobin and to buffer the protons by combining with it. So as carbon dioxide enters the systemic bloodstream, it causes more oxygen to diffuse from hemoglobin, which we know that as the Bohr effect. The dissociation of oxygen allows more carbon dioxide to combine with hemoglobin, and that's what we mean by the Haldane effect. There is a video that I posted on Canvas which helps you understand the difference between the Haldane effect and the Bohr effect, which you might find helpful. So the Haldane effect encourages carbon dioxide exchange in both the tissues and lungs. In the pulmonary circulation, the situation that we just described is reverse. Uptake of oxygen facilitates release of carbon dioxide. So as hemoglobin becomes saturated with oxygen, the protons release combines with bicarbonate, helping to unload carbon dioxide from the pulmonary blood. And finally, the last thing that we need to talk about is that typically the protons released during carbonic acid dissociation is buffered by hemoglobin and other proteins within the red blood cells or in plasma. The bicarbonate generated in the red blood cells diffuse into the plasma, where it acts as the alkaline reserve, part of the blood's carbonic acid bicarbonate buffer system, which we're going to detail in chapter 26. The carbonic acid bicarbonate buffer system is very important in resisting shifts in blood pH. So as an example, if the hydrogen ion concentrations in blood begins to rise, exits protons removed or is removed by combining with bicarbonate to form carbonic acid, which is a weak acid. If the proton concentration in blood drops below desirable levels, carbonic acid dissociates, releasing hydrogen ions and lowering the pH again. Changes in respiratory rate or depth can alter blood pH dramatically by altering the amount of carbonic acid in blood. So anytime you have slow, shallow breathing allows carbon dioxide to accumulate in blood, and as a result, carbonic acid levels increase and blood pH drops. Consequently, rapid, deep breathing quickly flushes carbon dioxide out of blood, reducing carbonic acid levels and increasing blood pH. So in this way, respiratory ventilation provides a fast-acting system to adjust blood pH and also the partial pressure of carbon dioxide when it's disturbed by metabolic factors. And respiratory adjustments play a major role in the acid-base balance of the blood, as we're going to discuss in a future chapter. So this concludes our notes or lecture video on the respiratory physiology.